Good morning, students, and Jai Swaminarayan. I hope your test went well. So, now let's move forward and start our new topic. Our next topic is force on a current carrying conductor in a magnetic field. Till now, what we did, we took one conductor and we applied some potential across it. And when the current was flowing in the conductor, we could detect the magnetic field around the conductor with the help of a magnetic compass. When we used to switch it on, the magnetic needle used to get deflected. This deflection showed us that there is some force when the current flows in a circuit, and that force was nothing but your magnetic field, which was generated when current flows through a conductor. Somewhere in near 1821, Ampere, a French scientist, have a thought in his mind that if a current carrying conductor is having some force and because of which the magnetic needle got deflected, then it is possible that the magnetic field or the magnet will also have some force on the current carrying conductor. And this is true because in ninth standard we studied Newton's third law of motion, in which we came to know that for every action there is equal and opposite reaction. So here, if the action is there because of the current in the conductor, then equal reaction should be there from the magnetic needle. So to know whether this was true or not, he performed one experiment in uniform magnetic field. What he did, he took uniform magnetic field and he placed one conductor in it. And he tried to find out whether there was some force because of the magnetic field on conductor or not. Here we can easily see in our previous setups, we can easily see that the current has some force because of which the magnetic needle used to get deflected. This needle used to get deflected easily because it was free to move. But our conductor was not free to move. So in this experiment, what he did, he kept the magnetic field as it is and he suspended the conductor. So before having a look towards its experiment, let us first know what is uniform magnetic field. So if I take a bar magnet, then in a bar magnet, these are my field lines from north to south, right? But as you can see here, on the poles, my magnetic field is very strong. The strength of my magnetic field is very strong. And as I go away, the strength of my magnetic field is not that strong. So, this magnetic field is not uniform. So, how to get this uniform magnetic field? You can get this uniform magnetic field with the help of a horseshoe magnet. So, this is how your horseshoe magnet looks. Right? This is my north pole and this is my south pole. Here also my magnetic field is directed from north pole to south pole. So these are few magnetic field lines. In the same way, I will have magnetic field lines here also. So these are my field lines which are uniform. So in this way, he got uniform magnetic field. There is one more way to get uniform magnetic field. Take two bar magnets and keep them apart. So this is my bar magnet 1 and this is my bar magnet 2. Now if I want to keep them apart, I need to fix them. So I fix them with help of some clap or something. Now you know opposite poles attracts. So there is some field between North Pole and South Pole. And this magnetic field is uniform. So in this way you can get uniform magnetic field. So there are two ways to get uniform magnetic field. That is with the help of a horseshoe magnet, or else you can place two magnets apart and then you can have uniform magnetic field. So with the help of this uniform magnetic field, Ampere performed one experiment to know whether there was force on a current carrying conductor in a magnetic field. So let's have a look towards his experiment. So this is how his experimental setup was. He took one horseshoe magnet and he fixed it. So here we have uniform magnetic field of horseshoe magnet. What he did, he placed one conductor perpendicular to the magnetic field. This conductor was freely suspended with the help of two wires. So this was like a swing which can move easily. So these two wires were connected to the battery. So when the current was on, it was flowing from this direction to this direction. That is, let us label as A and B. So the current was flowing from A to B. And the magnetic field was perpendicular. So if this is my magnetic field and my current was going from A to B, right? So this is 98 degree. So my current was perpendicular to the magnetic field. And as soon as I switch it on, my conductor got deflected and it went inside. It moved towards the right, which showed that there was a force on a conductor when it was placed in a magnetic field. A current carrying conductor, when there was a current in the conductor. As soon as we switch it off, it came back to the normal. So he did that again. Again he moved towards the left. Then he reversed the polarity of the conductor. So I am marking the reverse polarity with blue color marker. So this was my reversed current after reversing the direction of current. Again when we switch it on, the conductor again got deflected, but this time it got deflected on other side. So which shows that there was a force on a current carrying conductor, and that force depends on the direction of the current. Later on, what we did, we reversed the polarity of our magnet too. So now my magnetic field is going upwards. So again we did the same experiment and we found out that the force is not only dependent on the current in the conductor, it also depends on the magnetic field in which that conductor was placed. So after this successful experiment which proved that there was some force on the current carrying conductor in a magnetic field, another scientist named Fleming gave a rule to know in which direction the force is going to act. That rule is known as Fleming's left hand rule. So let's have a look towards Fleming's left hand rule. Now let us see Fleming's left hand rule to understand in which direction the force on a current carrying conductor acts when it is placed in a uniform magnetic field. So what you have to do, you have to take your left hand and in that your thumb will give you the direction of the force. Your index finger will give or will be along the direction of the magnetic field and your middle finger will be along the direction of the current. So these three should be perpendicular to each other. So if I see like this, then my middle finger and my index finger are perpendicular to each other. If I see like this, then my thumb and my index finger is perpendicular to each other. So if I take this combination like this, then all these three components are perpendicular to each other. Now, when I place or when I take a combination, let us take my current which is from left to right and my magnetic field which is moving upwards. So this is my magnetic field and this is my current. Now let us try to find out in which direction the force is going to apply. So my magnetic field is pointing upwards and my current is pointing left to right. Right? So this is my magnetic field and this is my current. They are perpendicular to each other. Now stretch your thumb perpendicular to your index finger and your thumb will give you the direction of the force which is going to act on the conductor. So my thumb is pointing outwards. So my conductor will get deflected outwards. So let us try to see. Now this blue pen is a conductor which is carrying some current and the tip is going to show you the direction of the current. So my current is in this direction and this is my magnetic field which is pointing upwards. So my magnetic field is pointing upwards and my current is pointing from left to right, this way, right? Now my force was outside, so this pen is going to get deflected outside. So this way you can find out in which direction the force is going to get applied when a current carrying conductor is placed in a magnetic field. It is hard to remember the direction, the magnetic field and a current. No, it's not. You should just know the father, mother, child rule. So, F for father, right? F is for father, then comes the mother and then comes the child. This is the order. So, F is the force, M is the magnetic field and C is the current. So your thumb is going to be your father, mother and child.